Chapter 5.4.2, the photoelectric effect. By the end of this section, you should be able to explain the photoelectric effect and experimental observations of it. So here is a very nice diagram explaining what is happening. We will see the details now. So by the end of this section, you should be able to do this. Explain the photoelectric effect and experimental observations of it. Understand how the photoelectric effect provides evidence for the photon model of light. Use the photoelectric effect equation. So this equation is very important. I will tell you the details also. So there are three things here in this equation, and this is the equation, actually this one. Okay, this is rearranged. So HF is the energy of the photon. We saw that in chapter 5.4.1, the previous lesson video. Phi is the work function, and this is the energy of the photoelectron. So let's see what that is. Here you can see what is happening. Now when this ultraviolet light falls on this metal surface, it removes electrons from this metal surface. If the energy, since the energy of this ultraviolet light is large enough, so part of the energy is used to remove the electron, the remaining amount of energy becomes the kinetic energy of the electron. So you can use the law of conservation of energy to help you understand this. Some of the energy is used to remove the electron. The remaining amount of energy is making the electron move out of the metal surface. That is the kinetic energy of the electron. So what happens is the energy of the photon is equal to the work function, which is the minimum amount of energy required to remove the electron from the metal surface, plus the kinetic energy of the electron. So we will see the details. And these electrons which are moving out of the metal surface when the light falls on it are called photoelectrons. Photoelectrons. So from the name itself, I think you can understand. Photon, like light falls on it, and then the electron is coming out of the metal surface, removed from the metal surface. That's why they are called photoelectrons. If ultraviolet light is shown onto a negatively charged zinc plate, see, when it is negatively charged, it will be easier because you have more negative charges or more electrons, then it will be easier to remove the electrons, but we'll see. Shown onto a negatively charged zinc plate, the plate loses its charge. So here this is a gold leaf electroscope. Again, you would have learned the details about the gold leaf electroscope in the O-level classes. I have also uploaded a video about the gold leaf electroscope. You can watch that under static electricity. All the details that you need to know about the gold leaf electroscope are there. How it works, how to charge it, how to find the charge of something using the gold leaf electroscope. All the details are there. How this leaf moves up or moves down. So we will see. Now what happens is, let's say this is negatively charged. This gold leaf electroscope, you can see here, is negatively charged. Now what happens is when light falls on it, the electrons are removed from the metal surface. This is the metal plate. And here this is insulation. So for more details, you can watch the video lesson on the gold leaf electroscope. So this is insulated. Then you have the metal rod here, and this is the gold leaf. Now when electrons are removed, what happens to the overall charge here? It decreases. When the overall charge decreases, the repulsion, now here this is all negative. This is negatively charged. In the beginning, these are all negatively charged. So negative, they repel. Like charges repel. You have learnt it already. Now when some of the electrons are removed from here, the repulsion decreases. Why? Because negative charges are removed. So if you have less negative charges repelling each other, the electrostatic force of repulsion is less. If you have more negative charges nearby, then the repulsion is more. So when electrons are removed, the repulsion here becomes less. Therefore the gold leaf electroscope deflects downwards. It falls downwards. Gold leaf falls immediately. The zinc plate is illuminated with ultraviolet light. Negatively charged zinc plate. See, this arrow indicates that the gold leaf is moving this way. Ultraviolet light source. If ultraviolet is shown onto a negatively charged zinc plate, the plate loses its charge. The explanation for this is that light causes electrons to leave the metal, removing the negative charge. The electrons that are released are called photoelectrons. So now you know again what photoelectrons are. Now these words are important. If you again scroll to the bottom of the subchapter 5.4.1, this chapter, you can see the definitions are given here. That makes it easier for you. Photoelectrons are electrons released from a metal surface as a result of its exposure to electromagnetic radiation. Now ultraviolet light is in the visible range of the electromagnetic spectrum. Remember the colors of the rainbow, the acronym ROIGBIV. When you learned about dispersion of light in the O-level class, when white light was passed through a prism, it caused the light to disperse. There was refraction and dispersion, 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 which gave you the spectrum of white light, the colors of the rainbow: red, orange, green, red, orange, yellow, ROIG, green, blue, indigo, violet. And indigo and violet are considered as one color, as violet in some textbooks. Anyway, however, variations on this experiment throw up some surprising observations. There is a certain minimum amount of energy that an electron needs in order to escape the surface of the metal it is in. This energy is called the work function and has the symbol phi. So let me write it and show you. That will make it easier for you. Alright, so here is basically what we have. This is the equation. Energy of the photon is equal to the work function plus the maximum kinetic energy of the photoelectron, and it is explained here. This is the equation. So what happens is, according to the law of energy, conservation of energy, energy cannot be created or destroyed. That means the energy of the photon that falls here onto this metal surface, the energy from that is absorbed by the electron, and part of that energy is used to remove the electron from the metal surface, because you know the electron, it's in the metallic bond, so there is some energy that is required to remove the electron. Now if the energy of the photon is greater than the work function, which is the minimum amount of energy required to remove the electron from the metal surface, then there is a remaining amount of energy. Now what happens to this energy? It is still in the it is there in the electron, and that gives the kinetic energy to the electron to move it out of the metal surface, which we call, then the electron is called a photoelectron. So you can see the law of conservation of energy is used here. Energy of the photon is equal to the work function plus the kinetic energy of the photoelectron. So energy of the photon, you know, is equal to HF. We saw it here earlier. And then phi is the work function. Remember, E equals HF. So F naught is the threshold frequency. Now we will see that threshold. You can see when F decreases, energy of the photon decreases. So if that electromagnetic radiation, now in this case it is ultraviolet light, but let's say there is some other electromagnetic radiation which has a lesser frequency than ultraviolet radiation, then the energy that those photons carry in those waves is lesser. So if it is less, now if this energy of the photon is less than the work function, no photoelectric emission takes place. The electrons are not removed from the metal surface. But if the energy of the photon, if this is equal to this, then this term has to be 0. So that means the electron is removed, but it doesn't come out of the metal surface. It's not emitted out. It's just removed and stays there, you can imagine. So if the energy of the photon, if this value is greater than the work function, that means the remaining amount of energy becomes the kinetic energy of the electron. So there is photoelectric emission. Electrons are emitted out of the metal surface. So this you can understand with the law of conservation of energy now. So let's go back to what we were learning. And here there is another diagram in this other book. You see, energy of the photon is absorbed, and then part of that energy you can see is the work function. It is used to remove the electron from the surface. Then the remaining amount of energy becomes the kinetic energy of that electron which escapes, which we call the photoelectrons, a photoelectron. A single photon may interact with a single electron to release it. Now this is also important. Two photons can't remove one electron. One photon can't remove two electrons. It's always one photon for one electron. So a single photon may interact with a single electron to release it. Okay, let's continue. So now you know what the work function is. However, variations on this experiment throw up some surprising observations. There is a certain minimum amount of energy that an electron needs in order to escape the surface of the metal it is in. This energy is called the work function, and it has the symbol phi. You can see it's also illustrated in this diagram. So to bring it out, this is the amount of energy needed, that is the work function. The wave theory of light would allow some of the wave energy to be passed to the electrons to enable them to gain the work function and escape. In wave theory, the energy carried by a wave depends on its amplitude. So if it's a wave, you know, the energy depends on the amplitude also. Now, for example, if you take easy way to understand is sound waves. The louder the sound means the greater the amplitude of the sound. So if the amplitude of sound waves is high, you will hear a loud sound. It carries more energy. That's why it hurts your ears. So when those vibrations in the air molecules are having a very large amplitude, and when they strike your eardrum, it causes your eardrum also to vibrate with a large amplitude, which causes pain. So the more energy the wave carries, and if you are receiving that, it will cause you pain. Okay, now for example, same thing, let's say some in the case of a bomb, for example, it's also carrying waves in there. So that is having a lot of energy, so it hurts you. Same thing with the sound. Loud sound have greater amplitude, so it can hurt you. So more energy is carried by a greater amplitude wave. In the wave theory, the energy carried by a wave depends on its amplitude, which for light means its brightness. So the wave theory could predict that any color of light, if made sufficiently bright, should enable the release of photoelectrons. Now that is not happening here. Now I told you it's one photon removing one electron. So the intensity doesn't affect this. So we will see that now in detail. So the wave theory would actually more, if you have more, then it will remove more electrons, but the energy of the photon is unaffected. That is actually also explained in the table here. See, this table explains that. See, wave model, photon model. So increasing the frequency of light increases the maximum kinetic energy of the electron. Now if you have looking at this, if the photons have a higher frequency, that means they have more energy. So this is a fixed amount. It's a work function, it's fixed for a certain metal. So that is fixed. That means the kinetic energy of the photoelectron will be greater. Okay, so increased frequency of light increases maximum kinetic energy of the photoelectrons. So wave model, it should be increasing intensity, but that doesn't happen. So if you increase the frequency, it doesn't produce more photoelectrons. It doesn't cause more photoelectrons. Instead, it causes the same number of photoelectrons but with a higher speed. So if it's the wave model, what should happen is it should increase intensity, not frequency. That increases energy of electrons. So photon model, higher frequency means more energetic photons. So electrons gain more energy and can move faster. So this table is quite important. Especially this is from the Cambridge book, so the Cambridge students should study this table. Okay, now we'll go back to this lesson. So the wave theory would predict that any the wave theory of light would allow some of the wave energy to be passed to the electrons to enable them to gain the work function and escape. In the wave theory, the energy carried by a wave depends on its amplitude, which for light means its brightness. So the wave theory would predict that any color of light, if made sufficiently bright, would enable the release of photoelectrons. Alternatively, if the wave were of smaller amplitude, it could shine for longer and slowly pass energy to the electrons until they had gained as much as the work function and escape. However, this is not what is observed. So this is not what is observed. So that means if you shine more light, that means if there are more photons falling on this, it will release more photoelectrons, but it doesn't have an effect on the kinetic energy of the photoelectron. I think that is clear. So imagine if it's ultraviolet light of a particular frequency that is falling on this, no matter how much, now imagine you have a bigger source to emit more ultraviolet light. Okay, so frequency of the ultraviolet light is constant, but you have more ultraviolet light falling on this. So that means you have more photons to remove more electrons. Remember, one photon removes one electron. So if you increase the intensity, that means if you have more photoelectrons falling on this metal surface, it will increase the number of photoelectrons, but it doesn't increase the kinetic energy of the photoelectron, because the kinetic energy of the photoelectron depends on the energy of the photon, which depends on the frequency of the light falling. So if you want to increase the kinetic energy of the electrons that are emitted, that is the photoelectrons, then you should have light with a higher frequency falling on that metal surface. I think this is clear now. Okay, so this table basically explains that. See, it's all explained here. Emission, see, observation emission of electrons happens as soon as light shines on the metal. See, photon model, wave model, there is a comparison in this table. A single photon is enough to release one electron. Okay, very intense light, wave model. And what is important here, like I said, is what I explained just now about the intensity and about the energy of a photon, and one photon always removing only one electron. Then threshold frequency of light is needed. For photoelectric emission to occur, there is a minimum amount of energy that is required, which is equal to the work function. So no matter how much photons fall on this metal surface, there will be no photoelectric emission if the frequency is less than the threshold frequency. If the energy of the photons is less than the work function, no matter how much light falls on that metal surface, there will be no photoelectric emission, because you need a minimum frequency for photoelectric emission to occur. That means it depends on the wavelength or the frequency of the photons of that light falling, frequency or wavelength of the light falling on the metal surface. Okay, so I think that's clear, and it is also summarized in this table. They are comparing the wave and the photon model here. Okay, so the wave theory would predict that any color of light, so I told you this is not the case. Any made sufficiently bright, so that means more intensity is higher, if made sufficiently bright, should enable the release of photoelectrons. Alternatively, if the wave were of small amplitude, it would shine for a longer and slowly pass energy to the electrons until they had gained as much as the work function and escape. However, this is not what is observed. See, the same negatively charged zinc plate cannot be discharged by red light. Okay, so remember the electromagnetic spectrum, you have radio waves, microwaves, infrared, and then you have visible region and ultraviolet. So infrared, in the visible region next to infrared you have red, and then ROYG, BIV, violet. Then violet, next to violet you have ultraviolet. So when you go towards from the red end to the ultraviolet or violet end, the wavelength decreases, frequency increases, so more energy. That's why with red light it won't cause photoelectric emission here, because red light has a longer wavelength or a smaller, or we can say lower frequency than ultraviolet light. So when frequency increases, look at this, then it's when the frequency increases, the energy of the photon is higher, or when the wavelength is shorter, the higher the frequency, the higher the energy of the photon. So that's why it doesn't work with red light, because red light has a longer wavelength, it has a lower frequency. That means energy of those photons of red light is less than the work function which is necessary to remove the electrons from the metal surface. The same negatively charged zinc plate cannot be discharged by red light, no matter how bright or how long the illumination. no photoelectrons are emitted under red light. There is a maximum wavelength for the light above which no photoelectrons are emitted. Remember, shorter the wavelength, greater the energy. Look at this, then it's easier. Okay, shorter the wavelength, greater the frequency, greater the energy. So that's why they say there is a here you can see there is a maximum wavelength for the light above which, so if the wavelength is greater than that, then the energy will be less. If the wavelength is greater, energy will be less. So there is a maximum wavelength for the light above which no photoelectrons are emitted. This can be thought of equivalently as a minimum frequency for the light, known as the threshold frequency. So that's why I wrote it with the naught here, f naught, hf naught, or 0 f naught. So this is the threshold frequency. If the photons have a frequency which is equal to this, then we can say the electron is just removed from the metal surface. But if this energy is greater than hf naught, photoelectric emission takes place. If hf is less than hf naught, no photoelectric emission takes place. We write that down later. Okay, so let's see the rest of this. Okay, so there are ways to investigate now. Like I mentioned, this is the experiment. It's actually starting here. If you charge a gold leaf electroscope, when then it will show a deflection on the gold leaf. If you place a zinc plate on top of the electroscope, the photoelectric effect will allow the electroscope to be discharged if it held a negative charge. So this is what I explained. If you shine ultraviolet light onto the zinc plate, the gold leaf will immediately fall. Why? Because negative charges are leaving. It reduces the repulsion here because you have less negative charges to repel each other, which means the electrostatic force of repulsion is less. It falls down due to its weight. Those electrons remaining on the gold leaf and electroscope stalk spread out more, so there is no longer enough mutual repulsion to hold up the gold leaf. You may need to clean the surface of the zinc as it oxidizes quite easily in air. So there may be a layer of oxide on top of the pure metal, stopping the light absorption. Okay, the explanation for these experimental observations can be summarized as: light travels as photons with a photon energy proportional to the frequency. So we saw that photon energy proportional to the frequency. Now this h is a constant, so we can say E is proportional to h. F E is proportional to F. H is a constant. It's a Planck's constant. It's a constant for the all cases, all waves. When a photon encounters an electron, it transfers all its energy to the electron, and the photon ceases to exist. So all the energy of the photon is absorbed. That's how we can write this equation. See, this is the energy of the photon. All of it is absorbed by the electron. So this side is for the electron, this side is for the photon. If an electron gains sufficient energy more than the work function, it can escape the surface of the metal as a photoelectron. Brighter illumination means more photons per second, which means a greater number of photoelectrons emitted per second. So this is what I said. Brighter means greater intensity. There are more photons falling on the metal surface. So more photons means more photoelectrons can be produced. More electrons can be removed from the metal surface. So if you have brighter illumination, that means more photons per second, which will mean a greater number of photoelectrons emitted per second. But the energy of each photoelectron remains the same because we are not increasing the frequency. We are having the same light source, but we have more of it falling. So the frequency is not changed. That's why the kinetic energy is unaffected here. If an electron does not gain sufficient energy from an encounter with a photon to escape the metal surface, it will transfer the energy gained from the photon to the metal as a whole before it can interact with another photon. Thus, if the photon energy is low, no photoelectrons are observed. So next page, and here I have already explained this. Now to help you all understand this better, let's go through this example. Well, I'll quickly read this so that everything is complete, you all are not missing anything. Einstein developed an equation to explain the photoelectric effect, which is based fundamentally on the conservation of energy. So I have explained all this. Now when I read this, it should be easy for you to understand. We have previously seen that the energy of a light photon can be found from E equals hf. An electron gaining this energy from a photon will have to use up the amount of energy equal to the work function in order to escape the metal surface. I have explained all this. If before that the electron needs to travel up to the surface from deeper in the metal, it will have used up some additional energy along the way. Only the remaining energy will be available to be used by the electron as kinetic energy. So I showed you this diagram also to help you understand it. So part of the energy is used to remove the electron. Then if there is additional energy, it will be the kinetic energy of the electron. See here, this is what I said. So if the frequency is the threshold frequency, like I said here, this is the equation. Now this is equal to hf naught, right? So it's if the frequency here is equal to the is equal to the threshold frequency, then this term is 0. That's how you get this. Okay, then what happens? The electron just escapes, it stays there. See that? Because this is hf naught now, which is the threshold frequency. hf is the threshold frequency. The electron is just removed, but you see here the difference. Here it is going out. Here in the second diagram, it stays there. Electron just escape, stay. Here it's going all the way out. See. So we can see these details also. Only the remaining energy will be available to be used by the electron as kinetic energy to fly away. Therefore, the kinetic energy that the electron can have on departure from the metal surface is less than or equal to the difference between the photon energy and the work function. So that's, if you rearrange, you get this. See, if you look at this equation, the kinetic energy here, if you move this term to this side, move this to this side, hf minus phi will be equal to the kinetic energy. Okay, so hf minus phi is the kinetic energy. Therefore, the kinetic energy that the electron can have on departure from the metal surface is less than or equal to the difference between the photon energy and the work function. The maximum possible kinetic energy, which is this, determines the maximum velocity of the photoelectron. So whatever that energy, the remaining amount of energy, will be the maximum energy that the electron has after it is removed from the metal surface. So that's why we call it maximum kinetic energy. So in the beginning it will have the maximum velocity, but what happens when it's released, when it is going out, then out of the metal surface, then there are air molecules, there can be some other particles which can slow it down. So in the beginning it has the maximum kinetic energy, but when it is going through the air, for example, the speed can decrease. Anyway, this is how we write it. Determines the maximum velocity. Yes, here I should have also written this as E max. Maybe I can do it. Yeah. So this is because this is the maximum kinetic energy, this will be E max, maximum velocity of the photoelectron. E for electron. Einstein's photoelectric effect equation then is this, or in direct conservation of energy terms, the photon energy hf is used by the electron partly to escape the metal surface. Okay, part of it is escape metal and partly as its kinetic energy. So this part. So a rearrangement of the equation is this. So this is what I showed you in the beginning. Now let's go through this question to help you understand the Einstein's photoelectric effect equation better. So this is the Einstein's photoelectric equation, and this what we call the electron escaping when the light falls on that surface is the photoelectric effect. Einstein's photoelectric effect equation. We are going to use it now. What is the work function of potassium if green light with a wavelength of 510 nanometers shines on it? Produces photoelectrons that have a maximum kinetic energy of 0.14 electron volts. Now this is not a SI unit, so you will have to convert it to joules, and this is the conversion factor. 1 electron volt is equal to this much, so you can use this conversion factor and convert electron volts to joules. The SI unit for terms in the photoelectric effect equation are all joules. You know, joule is a SI unit, but it is often used in units of electron volts. Remember that this. Okay, so you can use this value and convert from electron volts to joules. This value divided by 1 electron volt into this will cancel out the electron volt unit, which means this times this number here will give you the answer in joules for electron volts. So let's use this now. We are supposed to find phi. We can use this equation also. You can use this because this is what you learned, easy to understand. You can start with this instead of this and then rearrange. You get the same thing. Then if you use this or this, if you make phi the equation, the subject of the equation, this is what you get. But we are supposed to find the kinetic, we are supposed to find the work function. Alright, so first we can find we can use this equation directly. H is the Planck's constant, that will be given to you 6.63 into 10 to the power minus 34 joule seconds. And yeah, then you can, okay, first what they are doing is they are converting this to joules. You can see here I told you this multiplied by that will give you the answer in joules. Then you are supposed to find phi. Okay, phi. So we can find it now. Yeah, here I mean it's easier. Yeah, so here you can see see this HF what I showed previously. That's why I showed you this also. HF you can write it as HC over lambda. So HF HC over lambda. H is that, C is the speed of light in vacuum, which is approximately the same as in air. Now this is visible light range, so that means it is traveling at this speed. You can use that, and then they have not given us the frequency, that's why we are doing this and this way. Otherwise, if they had given the frequency, you can directly use HF, but they have given wavelength. So 510 nano is 10 to the power minus 9 meters. So here everything in SI units, that means this answer will also be in SI units. Now phi is equal to this. So you can see this equation. Now HF, that is this, which is this value there. So we write that there. Then kinetic energy of the electron, we found it here. That is that, and you get this, the work function. Very easy. You can do this by yourself also. Okay, the photoelectric cell experiment. So here we have something called stopping voltage. Again, this is also important. Then we have a graph. These work functions are constants for the metals. See, for these different examples of photoelectric work function values. Okay, now we will see the importance of this. So let's see what happens here. Looking at this, I think you can try to figure it out. Here we have ammeter. Now we write this microammeter like this because the current is very small. So we have to have the ammeter which can measure very small currents, such for example in microamperes. Then this is a voltmeter, so you can see it measures the potential difference across this photocell. Now again, photocell, from that also you can try to understand what this is about. See, photoelectrons. See, electrons are emitted, that's why they are photoelectrons. Then see, incident light, the photons are coming this way, it strikes this metal surface, and then electrons are emitted. Now what happens here, when there is movement of electrons here, that means there is a flow of current. So current is flowing like that, flowing this way, right? Here the electrons are going from here to here, it's going towards the negative terminal. This is a variable power supply. Remember, when you have the arrow on a symbol, if it was a symbol of a resistor, that means it's a variable resistor. So if you have this arrow on the power supply, that means it's a variable power supply. So you can adjust the potential difference across the photocell, across this. So what we are doing here is, we are shining light on this, incident light on this, that will cause the emission of photoelectrons. Okay, and when the electron is emitted, there will be a flow. The electrons are moving, right? So there will be a reading here. There will be a potential difference also we have. So what we are doing is we are increasing this value here, the variable power supply, so that it becomes more and more negative on this side. So negative and negative repels. So there will be a point where the potential difference across this is large enough to prevent the electrons coming to this side, because if you make this side more and more negative by adjusting the variable power supply, then the photoelectrons that are emitted from here are repelled. So there will be a point they will not be able to come to this side because of the high negative repulsion. Now at that point, the potential difference across this is the stopping potential. Okay, so that's basically it. Now then the reading here will become 0. So in the beginning there will be a reading here, and slowly we increase this until that drops to 0. At the point where it drops, that's the minimum potential difference to stop the current, which is stopping potential. So we will read this now to help you understand it better. A photoelectric effect cell experiment circuit. We could use the photoelectric effect equation to measure Planck's constant. So what's the point of this? To find the Planck's constant H. Remember this H and the work function. So from this we can plot a graph, and you can see where it intersects the axis. Using that we can find the gradient. See, gradient is the Planck's constant. The y-intercept is magnitude of that is the work function. So we will see. Now again, basic mathematics, you rearrange the equation and plot this and you will get the value, but we'll see how we do it. We could use the photoelectric effect equation to measure the Planck's constant and the work function. So point of this experiment, you can use it to measure the Planck's constant and the work function by plotting a graph like this. Planck's constant, now that is a constant always. It's no matter what the metal or whatever the case, that value doesn't change. That is a constant for the waves. But the work function depends on the metal. So you see, different metals have different work functions. In a vacuum, we can place the metal as the anode. In a vacuum, we place the metal as the anode. In a cell, see, we place the metal as the anode in a cell that has a gap to the cathode. So we have cathode and anode. See, between this one and this one, cathode and anode. See figure B. When we shine light of a known frequency onto the anode, so here is the anode. Now remember, for chemistry you would have learned anode and cathode. Anode attracts the anions, so it is positively charged. Now you can see here, this is the positive terminal, so that makes this the anode. So anode is something that, remember, for chemistry you would have learned, anode attracts the anions, so it has to be positively charged. Cathode attracts the cations, so cathode has to be negatively charged. So that means, see, this is the negative terminal. This here, this side is the cathode. So because I tell this because sometimes students confuse what is the cathode, what is the anode. They think that because the electrons are coming here, then maybe this is the cathode, but that's not the case. Okay, so remember this, important. When we shine light of a known frequency onto the anode, photoelectrons will be emitted and the current registered on the emitter. If we slowly increase the potential difference across the photocell using this variable power supply, eventually the anode will become sufficiently positive. So here this will, now either way we can say this side will be sufficiently negative, or we can say this side will be sufficiently positive so that it prevents the electrons from being emitted. Either way we can say it. So if we slowly increase the potential difference across the photocell, eventually the anode will become sufficiently positive. That means this will be sufficiently positive that all the photoelectrons will be stopped. So no photoelectrons emitted, because this is, we adjust this so that this becomes more and more positive, this side becomes more and more negative. Photoelectrons will be stopped and attracted back to it. See, they can be repelled from this side so that it goes back, or even if it's coming back here. Back to it, so the photoelectric current will be 0. The reading here will be 0. So this the potential difference at which this happens. Remember I told you that we can adjust this, and that will change the potential difference across this, because this voltmeter is measuring the potential difference across the variable power supply. Okay, so this is called the stopping potential, Vs. S for stopping, V for the potential difference, will give us the maximum kinetic energy of the photoelectrons from the definition of voltage. So in the beginning what happens, normally it is emitting, but we adjust this so that we can stop them coming out. So to make that happen, this potential difference should be such that it will equal the amount of kinetic energy given to this. So that's what we have here. So the maximum kinetic energy should be equal to the stopping potential, because it requires that much energy to come out. So if you are adjusting the potential difference here to prevent that happening, then you have to supply an equal amount of energy. Now when you learn the definition of voltage, you learn V equals W over Q. So that is what we are using here. I can also write it and show you. Okay, so here this is what you have learned in the O-level class. The power supplies, they push the electrons around the circuit. So battery, dynamo, generator, they all push the electrons around the circuit. So they're supplying energy to the electrons, we can say. Whereas resistors, cells and other components, they use the electrical energy from the electrons and convert it to other forms, maybe thermal energy, light energy, for example. So when we learn that, we learn this, and here volt is the energy supplied or the work done divided by the charge moved. So that is the energy supplied to the charges, and if we rearrange this, you get this. So this now you can check, you can compare with what we have here. See, E times Vs. So the energy, remember work done is energy transferred. You have learned this in the O-level class or 9-to-1 classes. Work done equals energy transferred. Then now Q, if it's an electron, we can use the letter E. Now in this case, what is it? The stopping potential. V is the stopping potential. S for stopping, V for potential. So that's how we get this equation which you see over here. Now I told you previously, the photoelectrons have a kinetic energy, half mv. I will write a small e there to indicate electron, then half mv squared, right? Now this is equal to this energy because it stops the electron, so it's supplying an equal amount of energy to keep it from moving. So that's how we get this equation. So let's continue that. This stopping voltage Vs will give us the maximum kinetic energy of the photoelectrons from the definition of voltage. If we use a range of light frequencies and find the stopping voltage for each, so we can adjust, we can use different f values and find the stopping potential for each. If we use a range of light frequencies and find the stopping voltage for each, we can plot a graph of the photoelectron maximum kinetic energy on the y-axis against frequency on the x-axis. Comparison with the equation for a straight line shows us that the graph should produce a straight best fit line and the gradient will be equal to the Planck's constant. So we will see how this is done. Now again, very simple. Now remember, this is equal to that. So again we have the photoelectric effect equation and we have it like this. So this is what we plot on the y-axis, see, and f, remember we are changing the frequency, so f we plot on the x-axis, the frequency. That means h, you know, is already a constant, and if you take for a certain metal, phi is constant, so you can see y equals mx plus c. So from this you can see that h is the gradient, this is the y-intercept. So since it's plus c, this will be plus minus phi. I will write it and show you, then it's easier. So therefore you can see the y-intercept will represent the value of the work function phi. Also, when the value of y is 0, the x-intercept, then the photon energy must equal the work function. Photon energy must equal the work function. See, so that is if you can see, you can have a look at this, you will understand it. Okay, so remember, when the kinetic energy is 0, see Y value, that is the kinetic energy of the photoelectron is 0, that means the F is the threshold frequency, because the electron is removed, but it's, you can imagine it's like staying there. So that means F is F0 here. We will write it in a better way, then you will understand. This means that the value of the x-intercept will give the threshold frequency. So you can use this to also find the threshold frequency for the anode metal. See, this is the anode metal. So we are finding it for this. Okay, this is placed here because this is the one giving out the electrons. Graphical analysis of the results from a photoelectric cell experiment can determine Planck's constant and the work function for the anode metal. Okay, so yeah, so then the definitions are important. Now we will write a note about this as well very quickly. Photoelectrons are electrons released from a metal surface as a result of its exposure to electromagnetic radiation. I think that's very clear. The work function is the minimum energy needed by an electron at the surface of a metal to escape from the metal. The threshold frequency, remember I used the symbol F0, for a given metal is the minimum frequency of electromagnetic radiation that can cause the emission of photoelectrons from the metal. So minimum frequency to cause photoelectric emission. Minimum frequency of the photon or electromagnetic radiation. The stopping voltage is an appropriately illuminated photoelectric cell. So illuminated means light is falling on it. This is the photoelectric cell. The stopping voltage is an appropriately illuminated photoelectric cell. In an appropriately illuminated photoelectric cell is the minimum voltage needed to reduce the photoelectric current to 0. Okay, so that's the end of that lesson on photoelectric effect. But to understand this better, now we will go through a few points here. Okay, so it will be we will discuss it separately because this is a lesson that I'm conducting to the students. So let's do that now, and I will end the recording here. The next lesson will be on electron diffraction and interference. Okay, so let's continue that end here, and we will write the note now.